It began as a faint hum, a whisper carried through the void, a signal no stronger than the hiss of cosmic background noise. Yet, beneath that static, hidden in a sliver of data from a deep space antenna in Canberra, something extraordinary emerged. The timestamp was routine. The origin, however, was not. It came from somewhere above the clouds of Jupiter, a world of perpetual storms, immense gravity, and mysteries older than Earth itself. For decades, Jupiter had been a familiar giant in our skies, a planet of legend and science alike. The ancients called it the king of gods. To modern scientists, it is a gravitational cornerstone of our solar system, a planet so massive that every orbiting body, from the smallest asteroid to the farthest comet, feels its pull. But for all our centuries of watching, measuring, and wondering, Jupiter remained a fortress. Beneath its swirling cloud tops, we have never truly seen. In the early years of planetary exploration, the idea of visiting Jupiter was a dream painted on chalkboards and star maps. Then, in 1972, a small spacecraft named Pioneer 10 changed everything. It slipped through the asteroid belt, the first to survive that journey, and sent back images that stunned the world. A gas giant striped with turbulence and light, a storm the size of Earth raging for centuries. It was the beginning of a long conversation between humanity and Jupiter, one that continues even now. Yet what we have learned about Jupiter and what we still don't reveals the paradox of exploration itself. Every probe we send out there brings us closer to understanding, but also deeper into mystery. The Voyagers, the Pioneers, Galileo, Juno, each mission peeled back one layer of the planet's grandeur, only to reveal more intricate questions beneath. Where does Jupiter's immense magnetic field come from? Why does its core defy every model we've built? And what are the strange lights that flicker at its poles? Auroras so powerful they outshine the sun in ultraviolet. The story you're about to hear is not just about Jupiter. It's about how human curiosity reshaped our understanding of the solar system, how we went from gazing at distant dots of light to building machines that can endure the radiation belts of a world 600 million kilometers away. It's about discovery and danger, triumph and error, silence and signal. And above all, it's about how, every time we think we have reached the edge of what we can know, the universe quietly reminds us. There is always more. In this journey, we'll trace the arc of exploration, from the first blurred images of Jupiter's moons to the dazzling infrared maps captured by modern probes. We'll descend into the swirling storms of Saturn and the frozen oceans of its moons. We'll walk the rusted plains of Mars, and finally, we'll turn back toward the pale blue that we call home, to ask a simple but unsettling question. What does it mean that Earth is, so far as we know, the only world where life took hold? But before we reach those questions, we must begin where the story begins, with the largest planet in the solar system. Because to understand the forces that shaped everything, from the orbit of our world to the conditions that allowed us to exist, we must first understand Jupiter. This is not merely a chronicle of missions and data. It is a narrative of human vision, of the fragile probes that dared to cross the solar winds, and of the scientists who deciphered the messages they carried home. It is the story of how a distant, swirling storm became a mirror for our own need to understand where we come from and where we might be headed. The hum detected in that faint radio signal, whether it was a quirk of plasma physics, a reflection of charged particles, or something we haven't yet learned to explain, was not an accident. It was a reminder. Jupiter is still speaking. And if we listen carefully, we might realize that the story of our solar system, and perhaps the story of life itself, began not on Earth, but in the storms of a distant giant. Welcome to the journey. Part 1. The First Eyes on Jupiter, Pioneer and the Grand Tour. Long before the shimmering images of Jupiter's great red spot appeared on television screens, there was only speculation and courage. In the early 1970s, space exploration was still a fragile enterprise. Rockets failed more often than they succeeded, and the farthest a spacecraft had ever traveled was Mars. Beyond that lay the asteroid belt, a region so poorly understood that many scientists believed any probe attempting to cross it would be pulverized by debris. And yet, in March 1972, a small hexagonal spacecraft named Pioneer 10 left Cape Canaveral, bound for Jupiter. Carried no weapons, no crew, and almost no chance of return. But attached to its aluminum frame was a small gold anodized plaque. A message for whoever might find it in the dark, millions of years hence. It bore the outline of a man and woman, the map of our solar system, and the faint pulse of human hope. At NASA's Jet Propulsion Laboratory, few truly understood the risks. The probe would have to travel 500 million kilometers, survive intense radiation fields, and operate far beyond the reach of any radio control. Everything depended on the success of its autonomous systems and the accuracy of its trajectory. We were literally flying blind, one engineer would later recall. Once we lost contact, there was nothing we could do but wait. By December 1973, Pioneer 10 reached Jupiter, and the waiting world saw, for the first time, a gas giant up close. The planet filled the probe's small black and white camera, its clouds rippling in bands of brown, white, and gold. The great red spot loomed enormous, a storm large enough to swallow Earth whole. But the most shocking discovery wasn't visual. It was invisible radiation. The spacecraft's detectors recorded an onslaught of charged particles 10,000 times stronger than anything near Earth. The readings came in bursts, overwhelming the sensors. Jupiter wasn't just a planet. It was a miniature sun of magnetism, a generator of radiation so fierce that it could scramble electronics from hundreds of thousands of kilometers away. The discovery nearly ended the next phase of exploration before it began. At the time, NASA was already building 2 new spacecraft, Voyager 1 and Voyager 2. They were the crown jewels of what scientists called the Grand Tour, a rare alignment of the outer planets that would occur only once every 176 years. If launched in 1977, the spacecraft could use the gravitational pull of each giant planet to slingshot to the next, Jupiter, Saturn, Uranus, and Neptune, without needing enormous amounts of fuel. It was a celestial domino effect, a perfect choreography of gravity. But the radiation readings from Pioneer 10 changed everything. The Voyager's intricate circuitry, far more advanced than the Pioneer's, could be destroyed within minutes of exposure. In a move that became NASA folklore, engineers rushed to grocery stores and hardware shops near JPL, buying every roll of aluminum foil they could find. They lined the critical cables and power buses of the spacecraft by hand, creating makeshift shields against Jupiter's deadly environment. It worked, barely. When Voyager 1 approached Jupiter in early 1979, its instruments captured what no human eye could ever see: a living, dynamic world of color and motion. The planet's clouds swirled like brushstrokes across a massive canvas of gas. The Great Red Spot turned out to be a gigantic, rotating vortex with winds exceeding 400 kilometers per hour. Lightning flashed within the clouds, illuminating structures hundreds of kilometers deep. But it wasn't Jupiter alone that shocked the world. The spacecraft's cameras turned toward the small dots of light orbiting the planet, the Galilean moons, discovered by Galileo in 1610, and revealed that each was a world of its own. Io, the innermost moon, was covered in yellows and oranges, its surface pocked with strange plumes. Scientists thought the image was corrupted, until one analyst realized the plumes were real. Io wasn't dead. It was erupting. Volcanic material was shooting hundreds of kilometers into space. For the first time in history, humanity had witnessed active volcanoes beyond Earth. Europa, by contrast, gleamed like glass. Its smooth, white surface was streaked with blue cracks, eerily similar to the pressure ridges of Earth's polar ice. Underneath, instruments hinted at something extraordinary: an ocean of liquid water, sealed beneath kilometers of frozen crust. The idea that life could exist in such a place, under the ice of a distant moon, ignited one of the most profound questions in planetary science. Could we be alone? When Voyager 2 followed months later, it confirmed and deepened these mysteries. It mapped Jupiter's magnetosphere, revealing invisible rings of charged particles trapped in vast belts around the planet. It captured time-lapse images of shifting storms, lightning, and auroras glowing at the poles. Immense curtains of energy driven by Jupiter's magnetic field. The data transformed our understanding of how a planet could behave without a solid surface. In a matter of months, the Voyager missions rewrote textbooks. They turned what was once a blurry disk in the telescope into a living, breathing system of storms, moons, and magnetic chaos. But the discoveries came at a price. As the probes passed through the radiation belts, their instruments flickered, and false commands began to appear. The environment around Jupiter was more extreme than any scientist had predicted. Still, Voyager 1 and Voyager 2 survived, propelled onward by the gravity of the planet they had come to study. As they left the Jovian system, each probe carried with it new data, new mysteries, and the momentum to explore even farther. Voyager 1 turned toward Saturn, while Voyager 2 would go on to Uranus and Neptune, completing the greatest journey in human history. When the last signal from Pioneer 10 reached Earth years later, it was faint, almost a ghost in the static. But its mission had succeeded beyond all expectation. Humanity had crossed the asteroid belt. We had touched the gravity of a world twice the mass of all the other planets combined. And in doing so, we had opened the door to a new era, the era of deep space exploration. The eyes of humanity had finally looked upon Jupiter. And Jupiter, in its silence, had looked back. Part 2. The Grand Tour continues. Saturn and the Rings of Ice. When Voyager 1 left Jupiter's gravitational pull in late 1979, its trajectory curved toward the next destination on its cosmic itinerary, Saturn. To the public, Jupiter had been the headline. To scientists, Saturn was the enigma waiting in its shadow. The planet's beauty had been admired since Galileo's time, but its true nature was a riddle wrapped in a halo of light. From Earth, Saturn's rings looked smooth, solid, like the grooves of a golden record circling the heavens. Yet early telescopic studies hinted at something far stranger. The rings were not solid at all, but composed of countless icy fragments, orbiting in an intricate balance of gravity and motion. How those rings formed, and why Saturn alone possessed such splendor, would become one of the central mysteries of the Voyager mission. As Voyager 1 approached the planet in November 1980, the first close-up images revealed a world of muted yellows and creams, striped by fast-moving winds that circled its equator at nearly 1,800 kilometers per hour. The planet's surface, if one could call it that, was a churning ocean of hydrogen and helium. Like Jupiter, Saturn was a gas giant with no solid ground. A vast globe of storms suspended above a metallic core buried under thousands of kilometers of atmosphere. Then the cameras turned toward the rings. What had once appeared smooth from Earth now resolved into exquisite structure. Thousands of distinct, concentric bands, some only a few kilometers wide. Between these bands were dark gaps, carved by invisible forces. One of the most striking discoveries was the presence of spokes, radial streaks that seemed to defy the orbital motion of the rings. Scientists debated whether they were electrostatically charged dust, lightning-induced shadows, or optical illusions. The truth was unclear, but the effect was mesmerizing. The rings shimmered not as static ornaments but as dynamic systems, changing, flickering, alive. Voyager's instruments also detected a new, faint ring far beyond the visible ones. The G ring, suggesting Saturn's ring system was more extensive than anyone had imagined. And then, as the probe's cameras swept across the planet's moons, Saturn revealed another of its secrets. Titan, the largest moon, glowed with an orange haze. It was the only moon in the solar system with a thick atmosphere. Hopes were high that the cameras would pierce the clouds and glimpse the surface, but all that came back was impenetrable fog. Titan's veil hid something extraordinary, a world with an atmosphere denser than Earth's, composed of nitrogen and methane. The chemical cocktail raised a haunting question. If Earth's life began in the chemistry of methane and ammonia billions of years ago, could Titan be a frozen echo of our own distant past? Voyager 1 had fulfilled its mission. Its slingshot past Saturn sent it on a trajectory out of the solar system, where it would drift forever into interstellar space. but its twin, Voyager 2, still had unfinished business. With a slower, more deliberate flight path, it would continue onward to Uranus and then Neptune, the first and only spacecraft ever to visit those worlds. By the time Voyager 2 reached Saturn in August 1981, Mission Control at NASA's Jet Propulsion Laboratory had perfected a kind of choreography. Each close encounter involved thousands of commands, pre-programmed weeks in advance, executed across millions of kilometers of empty space. There was no room for error. Every second counted. The images returned by Voyager 2 were sharper, richer in color, and more complete. They revealed ripples in the rings, subtle waves caused by the gravitational tug of Saturn's many moons. One moon in particular, Prometheus, acted as a shepherd, maintaining the inner edge of the F-ring, while another, Pandora, kept the outer edge in place. Their gravitational dance sculpted the ring's shape with mathematical precision. And then came a revelation that would change everything. The small moon Enceladus, only 500 kilometers across, appeared smooth and bright, too smooth, too bright. Unlike cratered worlds battered by time, Enceladus gleamed like a mirror. When Voyager's magnetometer passed over it, it detected a faint anomaly, a disturbance that hinted at a thin atmosphere or escaping vapor. It would take another spacecraft, decades later, to confirm what Voyager had only hinted. Enceladus was not dead. Beneath its icy crust, a warm ocean was venting water and organic molecules into space. By the end of 1981, both Voyagers had completed their Saturn flybys, leaving behind a transformed understanding of the planet and its rings. For the first time, humanity had seen Saturn not as a distant point of light, but as a living system, dynamic, complex, fragile. After Voyager 2 departed, Saturn would not receive another visitor for 23 years. The next probe to arrive would be a machine so ambitious, so sophisticated, that it represented an entire generation's leap in technology. Cassini. Launched in 1997, Cassini was a joint venture between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI. The spacecraft was enormous by planetary standards, carrying 12 major scientific instruments, a radar mapper, and even a small passenger Huygens, a probe designed to land on Titan. It took more than 6 years for Cassini to reach its destination, arriving in orbit around Saturn on July 1, 2004. The insertion burn, a delicate, hour-long maneuver, worked flawlessly. When the first data began to stream back, it was clear the mission would redefine everything we thought we knew about the Saturnian system. Cassini's instruments detected lightning storms larger than entire continents, auroras rippling around the poles, and an intricate web of gravitational interactions between the planet's moons and rings. But it was the moons, not the planet, that stole the show. On its second close pass of Enceladus, Cassini's magnetometer team noticed something uncanny, a deviation in the magnetic field, as if the moon were breathing. When they rerouted the spacecraft to fly just 175 kilometers above the surface, Cassini passed through a plume of vapor erupting from fissures near the moon's south pole, the so-called tiger stripes. The vapor contained water, salt, silica, and organic compounds, the fundamental ingredients for life. The discovery shocked the world. In a solar system once thought barren, there was now proof of a subsurface ocean warm, active, and possibly habitable. As for Titan, Cassini's partner probe, Huygens, descended through its orange clouds in January 2005, parachuting for 2.5 hours before landing softly on the surface. Its cameras captured a landscape of river channels, low hills, and pebbles made not of rock but water ice. Methane rain fell from the sky, carving valleys and filling lakes of liquid hydrocarbons. It was the first landing ever accomplished in the outer solar system, a frozen world that, paradoxically, looked eerily like Earth. For 13 years, Cassini orbited Saturn, looping between the rings, diving through their gaps, and transmitting more than 500,000 images. In 2017, low on fuel, it performed one final act of service. To avoid contaminating the moons that might harbor life, Cassini plunged into Saturn's atmosphere, burning up like a meteor. In its final moments, it transmitted data on the planet's magnetic field, atmosphere, and rings, information that scientists are still analyzing today. The signal faded, and with it, the voice of a spacecraft that had revealed a world. Yet Saturn's story didn't end there. Cassini's legacy was more than data. It was perspective. It showed us that even in the outer darkness of our solar system, beauty thrives, fragile, dynamic, alive. The Grand Tour had begun as a technical challenge. It ended as a human triumph. And beyond Saturn, another world awaited, colder, redder, and far more familiar. The next chapter of exploration would bring us closer to home, to Mars, and to the question that has haunted us for centuries. Could life have once walked there? Part 3: Red Dust and Silent Horizons. The long search for life on Mars. The red planet. For centuries, it has hovered in our night sky, a dim ember of rust and fire, a mirror of both our fears and our hopes. To the naked eye, it is only a bright orange star, wandering slowly among the constellations. But through the telescope, even in the earliest days of astronomy, Mars seemed different. Unlike the gas giants cloaked in storms, it showed a face: deserts, ice caps, and markings that shifted with the seasons. It looked, in the simplest sense, alive. The fascination began in the late 19th century, when Italian astronomer Giovanni Schiaparelli drew the first detailed map of Mars. He called the dark streaks canali, channels. The word was mistranslated into English as canals, igniting a frenzy. American astronomer Percival Lowell built an entire observatory in Arizona to study them. He was convinced they were artificial, the work of a dying civilization irrigating its last oases. His books inspired writers and dreamers alike. In the public imagination, Mars became a world of mystery and life. When the first space probes were launched in the 1960s, humanity was finally poised to find out the truth. But truth, as it turned out, would be far more complex than myth. The early missions were catastrophic. The Soviet Union's first attempts, Mars 1, Mars 2, Mars 3, either failed en route or crashed into the surface. NASA's Mariner 3 lost its solar panels. But in 1965, Mariner 4 succeeded. It flew past Mars and sent back 21 grainy images. What they showed shattered a century of imagination. A cold, cratered wasteland, more like the moon than Earth. No canals, no cities, no life, just silence and stone. Still, hope persisted. In 1971, Mariner 9 became the first spacecraft to orbit another planet. When it arrived, Mars was engulfed in a global dust storm that blotted out the surface entirely. For weeks, the probe circled above a world wrapped in red haze. Then, as the storm cleared, a different picture emerged. Volcanoes, vast canyons, dry river valleys. The planet wasn't lifeless, it was ancient. It had once been alive in a geological sense, shaped by fire and flood. The discoveries of Mariner 9 set the stage for a bold new step: landing on the Martian surface. NASA's twin Viking missions, launched in 1975, carried both orbiters and landers equipped with the most advanced life detection experiments ever built. When Viking 1 touched down in Chrysoplanitia on July 20, 1976, it sent back the first clear images from another planet's surface. A landscape of pink sky, red dust, and scattered boulders. For a moment, the world held its breath. The life detection experiments began their work. One of them, the labeled release experiment, produced a tantalizing result, a chemical reaction that looked eerily like metabolism. But subsequent tests failed to confirm it. The soil seemed rich in oxidants, chemicals that destroyed organic molecules before they could be detected. NASA's official conclusion was cautious but crushing. There was no clear evidence of life on Mars. And yet, in the decades that followed, those results would be re-examined again and again. Some researchers argued that the Viking experiments had, in fact, found traces of microbial life, but that the interpretation at the time was too conservative. The debate remains unresolved to this day. After the Viking missions, Mars exploration entered a long silence. For nearly 20 years, no probe was sent to the red planet. The cost was high, the scientific payoff uncertain. But when Mars returned to NASA's agenda in the 1990s, it was with a new philosophy: faster, better, cheaper. In 1997, Mars Pathfinder became the first successful lander since Viking. Its small rover, Sojourner, crawled across the rocks of Ares Vallis, analyzing their composition. The mission proved that mobility was the key. A rover could cover more ground, see more, learn more. It also proved something subtler: that Mars exploration could once again capture the public's imagination. Millions followed the rover's progress online. The idea of walking on Mars no longer felt like science fiction. In the early 2000s, a new generation of robotic explorers arrived: Spirit and Opportunity, twin rovers designed to search for signs of ancient water. They landed on opposite sides of the planet in 2004, using airbags to bounce safely to the surface. Both missions were meant to last 90 days. Spirit would survive for 6 years, Opportunity for 14. Their findings were transformative. Opportunity discovered layered rocks, evidence of sedimentary processes shaped by liquid water. In the crater where it landed, the rover found tiny spherical formations of hematite, nicknamed blueberries, that could only form in watery environments. Spirit, exploring Gusev crater, uncovered silica deposits and mineral salts, signs of hydrothermal activity. Mars, it seemed, had once been warm, wet, and dynamic conditions that could have supported life. Every discovery added another piece to a puzzle that stretched back billions of years. If Mars had rivers, lakes, and even hot springs, what happened to them? Where did the water go? The answer, scientists believed, lay hidden beneath the surface, locked as ice or trapped deep underground. In 2012, NASA landed its largest and most ambitious rover yet, Curiosity. The descent was a masterpiece of engineering: a supersonic parachute, a rocket-powered sky crane, and a controlled drop onto the floor of Gale crater. When the dust settled, the rover's mast rose, and its first panoramic image revealed the rim of Mount Sharp in the distance. Curiosity was more than a rover. It was a laboratory on wheels. Its instruments drilled into rocks, heated samples, and analyzed gases to identify carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the elemental building blocks of life. It found ancient lake beds, clay minerals formed in water, and complex organic molecules preserved in sediment. Even the atmosphere whispered secrets. Traces of methane appeared and disappeared with the seasons. Whether the methane was geological or biological in origin, no one could yet say. By the time InSight landed in 2018, Mars exploration had shifted from "was there life?" to "how did this world die?" InSight carried a seismometer to listen to the tremors beneath the surface, the first Marsquakes ever recorded. The data revealed a core still warm, but quiet, its internal energy fading over eons. Mars, once geologically alive, had simply run out of breath. But there were still surprises. The European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter detected subsurface ice at the poles and hints of briny water beneath them. Even now, the possibility of microbial life, dormant or hidden, remains one of science's most compelling questions. To search for life on Mars is, in a way, to search for ourselves. Every mission is a mirror held up to Earth, a reminder that planets are not static, that they live, evolve, and die. The dry riverbeds of Mars are echoes of what could happen to any world, even ours, under the wrong conditions. And yet, for all its desolation, Mars remains strangely familiar. A place of sunsets, seasons, and dust storms that rise like ghostly oceans. It is both a warning and an invitation. Our robots continue to wander its plains, tire tracks fading into red dust, carrying our questions with them. Was there ever life here? Could there be still? Perhaps, one day, a human voice will ask those questions in person. Standing beneath a salmon sky, the first footprints marking a world that once might have been like ours. Part 4: Beneath the Clouds. The Galileo mission and the heart of Jupiter in the twilight of the Cold War. As the Space Shuttle program rekindled humanity's reach for the stars, A new kind of spacecraft was taking shape in a sterile cleanroom at NASA's Jet Propulsion Laboratory. Its name was Galileo, a tribute to the man who, for centuries earlier, had first pointed a telescope toward Jupiter and discovered its 4 largest moons. If Pioneer and Voyager had been scouts, racing past the gas giant in fleeting glimpses, Galileo would become the first emissary to stay, to orbit Jupiter itself, to watch its storms evolve, and to dive into the mysteries hidden beneath its clouds. It was a mission of extraordinary ambition and equally extraordinary patience. Originally slated for launch in 1986, Galileo would be delayed again and again by tragedy and technical constraint. The Challenger disaster that year grounded the shuttle fleet, forcing NASA to redesign the mission completely. Instead of a powerful booster that could fling Galileo directly toward Jupiter, engineers were forced to rely on smaller, safer upper stages. The solution was as ingenious as it was circuitous. A gravity-assist route that would swing the probe around Venus, then Earth twice, stealing momentum from both planets to gain the speed needed to reach Jupiter. When Galileo finally launched aboard the Space Shuttle Atlantis on October 18, 1989, it carried the hopes of a generation of planetary scientists. The spacecraft was a marvel. A 2.2-ton machine powered by plutonium heat generators, equipped with cameras, spectrometers, magnetometers, and a 4.8-meter high-gain antenna folded like a silver umbrella. Once deployed in space, the antenna was meant to unfurl, a shimmering dish to beam back data from 500 million miles away. But when engineers sent the command to open it, the antenna jammed. For weeks, they tried everything, heating, vibrating, spinning the spacecraft, but the ribs of the umbrella refused to budge. Years in storage had caused the lubricant to dry out, freezing the delicate joints. The high-speed data link Galileo was built for was gone. The mission's heart had failed before it even began. It was a devastating blow, yet the team refused to give up. They reprogrammed the spacecraft to use its tiny low-gain antenna, capable of transmitting data at only a few bits per second, slower than a 1990s modem. Ingenious compression algorithms, error correction, and an Earth-based network of giant antennas allowed them to recover enough data to keep the mission alive. The crippled probe would continue, limping but undaunted. On its long journey, Galileo passed Venus, then Earth, capturing haunting images of our planet and moon from deep space. Along the way, it made history once more. In 1991, its instruments detected the first asteroid moon, a tiny companion orbiting the asteroid Ida, which it encountered en route to Jupiter. The little satellite was named Dactyl, after the mythical beings who aided the gods of Olympus. The name felt fitting. As Galileo approached Jupiter in late 1995, it deployed a small entry probe designed to dive directly into the planet's atmosphere. The probe's descent began on December 7th. For 61 minutes, it transmitted a torrent of data: pressure, temperature, wind speed, and composition. The results stunned scientists. Jupiter's atmosphere was far drier than expected, with almost no water vapor detected. Levels of helium and neon were lower than predicted, while evidence of internal heat hinted at turbulent convection deep below the visible clouds. The probe's final signal came as it was crushed and vaporized under pressures 20 times greater than those at Earth's surface. Then, Galileo itself began its orbital insertion burn, a 49-minute engine fire that slowed it enough to be captured by Jupiter's gravity. It was the first human-made object to orbit the largest planet in the solar system. What followed was a revelation. Each orbit of Galileo was a dance through a realm of radiation and magnetism. The spacecraft's instruments, constantly battered by high-energy electrons, recorded phenomena no one had anticipated. Magnetic storms raged across Jupiter's poles. Vast belts of trapped particles screamed through space at nearly the speed of light. Inside those fields, Galileo's circuits flickered and reset. Engineers on Earth worked miracles, rewriting software mid-flight to protect the failing systems. But the reward was immense. The data from Galileo transformed our understanding of the Jovian system. It revealed that Ganymede, Jupiter's largest moon, had its own magnetic field, the only moon in the solar system known to possess one. Beneath its icy crust lay an ocean sandwiched between layers of ice. Europa, 2. Showed signs of a vast subsurface sea, its smooth surface crisscrossed by ridges resembling pressure fractures in Earth's polar ice caps. When Galileo passed close to the Moon, its magnetometer detected subtle variations that hinted at conductive salt water beneath the ice. Later analysis would even uncover evidence of plumes, jets of vapor erupting from cracks in Europa's shell. Io, on the other hand, was chaos incarnate. Galileo captured eruptions hurling molten sulfur hundreds of kilometers into space, painting the Moon in yellows and reds. The tidal forces from Jupiter's gravity pulled Io's interior like taffy, generating heat that made it the most volcanically active body in the solar system. But it was not only the moons that surprised scientists. Galileo's measurements of Jupiter's magnetic field, atmosphere, and internal structure defied models. The field was more lopsided than predicted, and its source seemed to extend deep into metallic hydrogen layers where pressures crushed atoms into fluid metal. The planet's auroras, captured in ultraviolet and infrared, glowed like cosmic furnaces, driven not just by the solar wind, but by the immense rotation of Jupiter's magnetosphere itself. Every orbit brought both discovery and danger. The radiation near Jupiter was merciless. Circuits degraded, sensors glitched, and onboard memory occasionally erased itself. Engineers invented ways to command the spacecraft through safe modes, brief hibernations that allowed systems to recover. It was as much a human triumph as a technical one, the persistence of people guiding a distant machine through the most hostile environment ever explored. Over 8 years, Galileo completed 35 orbits, visiting almost every major moon and filling in details that the Voyagers could only glimpse. By the early 2000s, the mission was nearing its end. Power was fading, memory was damaged, and radiation had taken its toll. Yet there remained one final act, a decision born of both caution and reverence. To prevent any possibility of contaminating Europa's ocean with earthly microbes, NASA commanded Galileo to plunge into Jupiter's atmosphere. On September 21, 2003, the spacecraft entered the planet it had studied for nearly a decade. As it fell, it transmitted data until the surrounding pressure and heat tore it apart. Its final message reached Earth 52 minutes later, a whisper from 600 million kilometers away. Galileo was gone, but what it left behind reshaped planetary science forever. It had shown us oceans beneath ice, volcanoes beyond Earth, and magnetic fields that defied logic. More than that, it had proven something profoundly human. That knowledge, even when carried on fragile circuits across impossible distances, can survive and illuminate the darkness. In the years that followed, the lessons of Galileo would inspire a new generation of spacecraft. One of them, powered not by plutonium but by sunlight, would return to Jupiter to finish the story Galileo had begun, to fly not through its equator, but above its poles, and to peer deep into the heart of the storm. That mission would be called Juno. Part 5, The Polar Voyager. Juno and the New Face of Jupiter in August 2011. Beneath a Florida dawn streaked with vapor and thunder, an Atlas V rocket lifted from Cape Canaveral carrying a new emissary to the outer solar system. Its destination was the same giant that had humbled Pioneer, Voyager, and Galileo, but this time humanity was coming prepared. The spacecraft's name was Juno, and its mission was as poetic as it was scientific: to uncover the secrets of Jupiter's origin, structure, and soul. Unlike its predecessors, Juno would not skim the equator or linger near the planet's moons. Instead, it would take a path never before attempted: a polar orbit. From there, it would pass from north to south over Jupiter's poles, piercing the veil of clouds and mapping the planet's interior through magnetic and gravitational fields. If Galileo was the explorer who circled a fortress, Juno would be the spy who slipped over its walls. Everything about Juno was designed for endurance. Its electronics were encased in a titanium vault, shielding them from radiation doses that could fry an unprotected computer in hours. Its instruments, 9 in all, ranged from cameras and microwave sensors to magnetometers and plasma analyzers. But perhaps the most revolutionary feature was what it lacked: a nuclear generator. For the first time, a spacecraft bound for Jupiter would rely solely on solar power. At that distance from the Sun, where light is only 4% as strong as on Earth, the panels had to be immense, each one nearly 9 meters long. Together they stretched wider than a basketball court, making Juno one of the largest interplanetary spacecraft ever built. After launch, Juno followed a looping trajectory that took it past Mars and back toward Earth, stealing a gravitational boost that added 14,000 kilometers per hour to its velocity. From there, it coasted silently through the cold, dark gulf beyond the asteroid belt. For nearly 5 years, engineers and scientists waited, their eyes fixed on a countdown that would end in a single moment of peril, the Jupiter orbit insertion. On July 4, 2016, Juno arrived. That day, mission control at the Jet Propulsion Laboratory was tense and quiet. At 10:30 p.m. Pacific Time, a command signal sent 48 minutes earlier, traveling at the speed of light across 800 million kilometers, reached Juno. The spacecraft turned its main engine toward the direction of motion and fired. For 35 minutes, it slowed itself just enough to be captured by Jupiter's gravity. There was no real-time control, no correction, only faith in years of calculations. Then a tone came through. It was faint, but unmistakable. Juno had survived the burn. It was in orbit. Applause erupted in mission control, engineers embracing, tears falling quietly behind screens. Humanity had returned to Jupiter. The view from above the planet's north pole was unlike anything seen before. The familiar horizontal bands of color disappeared, replaced by a kaleidoscope of swirling storms arranged in a circular pattern. A cyclone at the center, encircled by 8 smaller ones, each rotating in harmony without merging or colliding. At the South Pole, a mirror image appeared, 5 storms encircling a central vortex. No one understood how such structures could remain stable. Jupiter was rewriting the rules of atmospheric dynamics. With every 53-day orbit, Juno dove perilously close to the planet, skimming just 4,000 kilometers above the cloud tops, then swung far out again to minimize radiation exposure. During each pass, its instruments gathered terabytes of data. The microwave radiometer peered hundreds of kilometers below the visible clouds, mapping heat and moisture patterns. The magnetometer traced the invisible contours of the planet's magnetic field. And JunoCam, the mission's modest public outreach camera, captured breathtaking portraits of storms twisting like oil on water, images that artists and scientists alike would process and share around the world. Then came the biggest surprise. For decades, scientists had assumed that Jupiter's magnetic field was generated by a dynamo effect deep within its metallic hydrogen core, much like Earth's. But Juno's measurements told a different story. The field was uneven, patchy, lumpy. As one researcher put it, much stronger in some regions than others. Its source seemed to lie not at a single central core, but higher up, perhaps in a layer of metallic hydrogen mixed with ammonia and water. This meant that Jupiter's interior was more complex and more chaotic than any model had predicted. Equally mysterious was the nature of the planet's famous Great Red Spot. For centuries, astronomers had watched it drift around the planet, sometimes shrinking, sometimes intensifying, but always enduring. With its microwave sensors, Juno peered deep into the storm and discovered that it extended nearly 350 kilometers below the clouds, far deeper than expected, and that the temperatures rose dramatically with depth. Unlike hurricanes on Earth, which draw energy from surface heat, the red spot seemed to be powered from within, a monument of turbulence fed by the planet's own internal furnace. But even as the science dazzled, the mission was nearly undone by a single glitch. After Juno's second orbit, engineers noticed irregularities in the helium valves controlling its main engine. If the problem worsened, a planned maneuver to shorten the orbit period from 53 days to 14 could end catastrophically. After weeks of deliberation, the team made a painful decision: cancel the burn and keep the long orbit. It meant fewer close passes per year, but also a longer mission lifespan. The choice proved wise. A day after the decision, Juno entered safe mode, shutting down all instruments due to a data transfer anomaly. For tense hours, communication flickered. Then, slowly, the spacecraft recovered. The ghost of Galileo's radiation troubles still lingered, but this time, the story didn't end in silence. Since that moment, Juno has continued its orbits, each one a breathtaking dive through radiation belts strong enough to kill a human in seconds. Its discoveries have reshaped our understanding not just of Jupiter, but of how giant planets form. By studying variations in the gravitational field, scientists detected hints of a fuzzy core, one that might contain dissolved heavy elements mixed throughout, rather than a solid heart. This suggested that Jupiter may have experienced a violent collision during its formation, perhaps with another planetary embryo the size of Earth. Meanwhile, Juno's images of the auroras blazing above the poles stunned researchers. These shimmering ovals of light, caused by charged particles spiraling along magnetic field lines, were unlike anything on Earth. They pulsed with energies thousands of times greater than terrestrial auroras, driven not by the solar wind but by Jupiter's own rapid rotation. The planet, spinning once every 10 hours, acted like a massive dynamo, whipping up magnetic storms that could power entire civilizations. Yet, beneath all the science, Juno was also something more, a work of art, a machine built not just to measure but to witness. The swirling blues and whites of Jupiter's clouds, seen from above, resembled abstract paintings. Even the mission's engineers described the images as emotionally disorienting. They were beautiful in a way that no data graph could capture, a reminder that exploration is as much about awe as it is about analysis. As Juno continued its mission, NASA extended its timeline again and again, allowing it to fly closer to the moons, Ganymede, Europa, and Io, capturing high-resolution images and sampling the charged plasma around them. Each pass brought new mysteries: electric currents linking moons to the planet, auroras flickering in rhythm with Io's orbit, magnetic footprints imprinted in the atmosphere. But the story of Juno is not yet over. When its mission finally ends, as all missions must, NASA will command it to plunge into Jupiter's depths, joining Galileo in the eternal storm. It will burn and vanish, but its data and its vision will endure. From the small telescopes of Galileo Galilei to the titanium vault of Juno, the arc of discovery has spanned for centuries. We have seen Jupiter not as a mere planet, but as a world of storms, magnetism, and strange order, a cosmic laboratory where the laws of nature reveal their most extreme forms. And even now, as Juno circles high above the cloud tops, there is a growing sense among scientists that this is not the end of the story, but the beginning of another. Because somewhere in the shadow of that great planet, another target is coming into focus, a world of ice and light that may hold the answers to the oldest question of all. Part 6. The Ocean Beneath. Europa and the search for life beyond Earth in the cold darkness that orbits Jupiter. There is a moon that glows like a frozen pearl. Smooth, bright, and streaked with delicate fractures, Europa is unlike any world in the solar system. At first glance, it appears lifeless, a sphere of ice, airless and silent. But beneath that ice, hidden from view, lies something extraordinary. An ocean deeper than all of Earth's seas combined. For decades, Europa had been a footnote to Jupiter's grandeur. The Voyager spacecraft first revealed its cracked, icy surface in 1979, puzzling scientists with its lack of craters. A young researcher at the time, Dr. Richard Terrell, noticed the pattern of lines, brownish streaks that ran across the entire moon, crossing each other like scars on glass. It looked as though someone had taken Europa, he said, and stretched its skin until it broke. That stretching, they realized, came from Jupiter's gravity. Europa, caught in the massive planet's tidal grip, flexed and strained as it orbited. The constant kneading generated heat deep inside, enough, perhaps, to melt the ice below. The idea seemed almost too wild to believe, a warm ocean beneath a frozen shell. But the evidence was mounting. In the 1990s, NASA's Galileo spacecraft flew close to Europa several times, measuring subtle variations in the magnetic field around it. The readings didn't match what a solid ice body would produce. Instead, they hinted at a conductive layer, most likely a salty, liquid ocean. When Galileo's camera captured chaotic terrains where blocks of ice appeared to have broken, drifted, and refrozen, the case grew even stronger. Europa was not static. It was alive in motion. The idea of a subsurface ocean changed everything. For the first time, scientists could imagine life beyond Earth, not in distant exoplanets or exotic atmospheres, but right here in our own solar system. Europa's ocean, sealed beneath 10 to 20 kilometers of ice, might be in direct contact with a rocky seafloor. If hydrothermal vents existed there, like the ones on Earth's ocean bottoms, they could provide energy and nutrients. On Earth, such vents teem with life. Tube worms, bacteria, entire ecosystems thriving without sunlight. If it can happen here, why not there? But Europa's secrets were not easy to reach. The surface temperature averages minus 160 degrees Celsius, and the radiation from Jupiter's magnetosphere is lethal, enough to kill a human in minutes. Any future mission would need to survive both extremes, the deep freeze and the invisible storm. After Galileo's mission ended, NASA scientists began designing new spacecraft specifically for Europa. For years, funding and politics delayed progress, but the dream refused to die. In the early 2010s, evidence from the Hubble Space Telescope reignited excitement. Faint plumes of water vapor, erupting hundreds of kilometers above the surface. These geysers, if confirmed, could allow a probe to sample Europa's ocean without drilling through the ice. It was the discovery everyone had been waiting for. Subsequent observations strengthened the case. Spectroscopic data revealed hints of hydrogen and oxygen, consistent with water vapor. Images taken months apart showed the same regions flaring and fading, suggesting active geysers. And then came confirmation from a surprising source. Galileo's old data, reanalyzed decades later, showed a magnetic blip precisely where a plume would have disturbed the surrounding field. The spacecraft had flown through one without realizing it. By 2025, the stage was set for a new chapter. NASA's Europa Clipper mission, scheduled for launch in the late 2020s, would orbit Jupiter and make dozens of close flybys of Europa. Its instruments would map the surface in unprecedented detail, measure the ice's thickness, and sniff for organic molecules in any plumes it passed through. The European Space Agency, too, was preparing its own mission JUICE, the Jupiter Icy Moons Explorer. Together, these spacecraft would attempt to answer one of the most profound questions in science. Could something be swimming beneath that ice? To understand what that means, it helps to look at Earth's own analogs. In Antarctica, scientists have drilled through kilometers of ice to reach buried lakes like Vostok and Whillans. Despite total darkness and crushing pressure, they found microbial life, cells clinging to minerals, feeding on chemical energy. These discoveries proved that sunlight is not essential for biology. Life can adapt, endure, and flourish in the most extreme isolation. Europa, in that sense, is not alien at all. It is familiar. It mirrors our own deep oceans, vast, hidden, sustaining. Still, the obstacles to exploring it directly are immense. Drilling through kilometers of ice in an environment colder than nitrogen's freezing point would require technology far beyond our current reach. Communication through thick ice would be nearly impossible. Even sterilization poses challenges. No one wants to contaminate a pristine extraterrestrial ecosystem with Earth microbes. And yet, the dream persists. Engineers sketch designs for cryobots, autonomous probes that could melt their way down through the ice, trailing communication tethers as they descend. At the bottom, they would release hydrobots, small submersibles that could navigate the ocean, searching for heat sources, organic compounds, or even movement. Sounds like science fiction, but so did the idea of flight once. The scientific stakes are immense. If even a single cell is found on Europa, one microbe that evolved independently, it would prove that life is not a rare cosmic accident. It would mean that biology is a natural consequence of chemistry, wherever conditions allow it. The implications would ripple far beyond science, reshaping philosophy, religion, and our sense of solitude in the universe. Europa also carries poetic resonance. In myth, Europa was a mortal woman carried across the sea by Zeus, the Greek name for Jupiter. Now, in a quiet echo of that legend, the moon that bears her name may carry the seeds of a second Genesis across the cosmic ocean. In the meantime, the Europa Clipper and JUICE missions will do what they can from orbit, mapping the ice, tasting the plumes, and searching for chemical signatures of life. They may not answer the question fully, but they will narrow the possibilities and prepare the way for what comes next. And as they orbit Jupiter, they will continue to reveal how interconnected these moons are. Radiation from the planet's magnetic field bombards Europa's surface, splitting water into hydrogen and oxygen, which then recombine and cycle back into space. The moon is part of a vast system of exchange, a chemical dialogue between ice, magnetism, and light. In that sense, Europa is not just a moon orbiting Jupiter. It is part of Jupiter's living machinery, a dynamic participant in the symphony of the Jovian system. Its surface cracks and heals. Its ocean swells and shifts. Its geysers breathe. Somewhere beneath that frozen crust, in the darkness where no sunlight ever reaches, there could be warmth. There could be motion. There could be life. And if that is true, then the story of life in our solar system may not belong only to Earth. It may be a melody played across worlds, in oceans that never see the sky. Europa waits in silence, turning slowly in Jupiter's glow, its secret ocean glimmering in the dark. But Europa is not the only moon whispering hints of habitability. Farther out, circling Saturn, another icy world has begun to tell its own story. A world that sprays its ocean into space for all to see. That world is Enceladus. Part 7, the cryovolcanic world. Enceladus and the blueprint for life. If Europa is the quiet enigma of Jupiter, then Enceladus is Saturn's whisper made visible. A frozen world that shouts its mystery into the cosmos. Barely 500 kilometers across, smaller than the British Isles, Enceladus should have been insignificant. Just another icy rock circling the ringed planet. Yet, against all expectations, it turned out to be one of the most extraordinary bodies in the solar system. The story begins in 2005, with NASA's Cassini spacecraft looping through the Saturnian system. For months, the mission had mapped Saturn's rings, moons, and magnetic fields in exquisite detail. Enceladus, at first, was little more than a target of convenience, a minor stop in the grand tour. But as Cassini passed by, its instruments recorded something strange. A faint haze, a shimmering mist near the moon's south pole. When the spacecraft adjusted its trajectory for a closer look, the truth emerged. Geysers, towering plumes of vapor and ice, were erupting from long fissures in the surface, spraying hundreds of kilometers into space. The cracks, soon dubbed the tiger stripes, glowed faintly in the infrared, revealing temperatures tens of degrees warmer than their surroundings. Something beneath the ice was alive with heat. The discovery shocked scientists. Until then, Saturn's moons were thought to be geologically dead, ancient, frozen remnants from the birth of the solar system. Yet here was a world smaller than the state of Arizona, defying that assumption. It was active, dynamic, even volcanic, though its volcanoes spouted not molten rock, but water and organic molecules. In the months that followed, Cassini flew through those plumes again and again, sampling the particles with its onboard instruments. The results were nothing short of astonishing. The vapor contained water, carbon dioxide, ammonia, methane, salts, and complex organic compounds, the chemical ingredients necessary for life. Even more compelling was the discovery of silica nanoparticles, the kind that form only when hot water meets rock, precisely the signature of hydrothermal activity at the seafloor. This meant one thing. Beneath Enceladus's frozen crust lay a liquid ocean, heated from below by the friction of Saturn's immense gravity. As the moon's slightly elliptical orbit stretched and compressed it, internal stresses generated heat, preventing the ocean from freezing solid. The same tidal forces that shaped its orbit also kept it geologically alive. It was an astonishing convergence of physics and biology, a world where tidal flexing, chemistry, and heat had conspired to create a potentially habitable environment. Dr. Carolyn Porco, leader of Cassini's imaging team, described the moment vividly. "We realized we were looking at a place where the conditions for life exist right now. Not in the distant past, but in the present." The idea of life beneath Enceladus's ice was no longer speculation. It was a testable hypothesis. The plumes, reaching into space, offered a direct pathway to the ocean below. No drilling, no landing. A spacecraft could simply fly through the vapor and sample it, an invitation written in frost and light. As Cassini's mission continued, it became clear that Enceladus wasn't just venting water. It was feeding Saturn's E-ring, a faint, broad ring of microscopic ice particles encircling the planet. The moon, in essence, was creating a ring system on its own, turning its internal ocean into a celestial fountain. Every orbit, it sprayed part of itself into the void, and every time, gravity brought some of that material back down as snow, resurfacing the world in brilliance. That's why Enceladus gleams so brightly. It's constantly renewing itself. Its surface reflects nearly all the sunlight it receives, making it one of the most reflective objects in the solar system. By the time Cassini ended its mission in 2017, scientists had enough data to sketch a portrait of Enceladus unlike anything else in the cosmic catalog. Beneath its ice lies a global ocean, possibly 30 to 40 kilometers deep, resting atop a rocky core. At the ocean floor, hydrothermal vents likely spew mineral-rich water heated to hundreds of degrees Celsius. These vents could provide both energy and chemistry for microbial life, just as they do on Earth's ocean floor. If any place beyond Earth harbors living organisms today, Enceladus is near the top of the list. And yet, the mystery deepens. Despite all that data, one crucial question remains unanswered. How much organic chemistry is happening there? The molecules Cassini detected, methane, complex hydrocarbons, could be produced by either geological or biological processes. On Earth, hydrothermal vents teem with microbes that produce methane as a byproduct of metabolism. But non-biological reactions, such as serpentinization, water reacting with certain rocks, could also explain the readings. To distinguish one from the other, scientists would need more precise measurements, instruments capable of detecting isotopic ratios or specific amino acids. For now, we can only speculate. Still, speculation has power. Enceladus has transformed our conception of where life might thrive. Before its discovery, the habitable zone was thought to be limited to the warm region around a star where liquid water could exist on a planet's surface. Enceladus shattered that idea. Here, 1.4 billion kilometers from the Sun, far beyond the traditional habitable zone, a tiny moon maintains liquid water, warmth, and chemistry, all powered not by sunlight, but by tidal energy. Life, it seems, might need far less than we imagined. The implications ripple outward. If such conditions exist around Saturn, they might also exist around other gas giants, not just in our solar system but in others. Astronomers now suspect that subsurface oceans may be common throughout the galaxy, hidden beneath ice, insulated from the cold of interstellar space. In the cosmic inventory of potential habitats, icy moons may outnumber Earth-like planets 1,000 to 1. Plans for a return mission to Enceladus are already on the drawing board. Concepts like Enceladus Orbolander envision a spacecraft that would orbit the moon, fly through its plumes repeatedly, and then land on the surface near the tiger stripes. There, it could analyze fresh-fallen particles, looking for complex organic compounds, cell membranes, or even amino acid patterns. Such a discovery, even a single microbial cell, would transform not just planetary science but human self-understanding. It would mean that life emerged independently in two separate places within one solar system. If it happened twice here, it must happen everywhere. And yet, beyond the scientific ambition lies something profoundly human. When the Cassini spacecraft made its final plunge into Saturn's atmosphere, mission control went silent. The last signal faded, and with it ended 13 years of exploration. But for many, Enceladus had already changed everything. It reminded us that life might not require sunlight, that warmth can arise from motion, and that even the smallest worlds can harbor oceans vast enough to hold secrets older than Earth itself. In the quiet glow of Saturn's reflected light, Enceladus continues to vent its icy breath into the void, a frozen whisper of possibility, drifting among the rings. And as scientists turn their gaze outward, they begin to wonder, if oceans can exist beneath ice, what about the countless exoplanets and exomoons beyond our sun? Are some of them oceans too vast, unseen, alive? The search for life, once confined to Earth and Mars, was expanding into a new frontier, the galaxy itself. Part 8. The Great Silence. Exoplanets, signals, and the expanding search for life. When we first looked up at the stars, we assumed they were distant suns. What we didn't know, what no one could have known, was just how many worlds were hiding among them. For most of human history, the idea of planets around other stars was speculation, a poetic notion more than a scientific one. Then, at the turn of the 21st century, the speculation became reality. In 1995, a small team led by Michel Mayor and Didier Queloz at the University of Geneva detected something extraordinary. A planet orbiting a star called 51 Pegasi, 50 light-years away. They had found it not by seeing it directly, but by watching the star's light wobble, subtly pulled by the gravity of an unseen companion. It was the first confirmed detection of an exoplanet, and it changed everything. The planet, now known as 51 Pegasi b, was unlike anything in our solar system. It was a hot Jupiter, a gas giant orbiting so close to its star that a year lasted only 4 days. Its atmosphere probably boiled with metallic vapor. But the significance wasn't the planet itself. It was the proof that other solar systems existed. Within a decade, new methods multiplied discoveries. The Kepler Space Telescope, launched in 2009, revolutionized the search. Instead of looking for stellar wobbles, Kepler stared fixedly at a single patch of sky, watching for the tiny dimming of stars as planets crossed in front of them. In 4 years, it identified over 2,600 confirmed worlds and thousands more candidates. Some were giants hugging their stars, others small and rocky. Some orbited red dwarfs in clusters, others circled binary systems. Just a few, lay in what astronomers call the habitable zone, where temperatures might allow liquid water to exist. For the first time, we could begin to count the possible Earths. The numbers were staggering. Statistically, there could be hundreds of billions of planets in our galaxy alone, with perhaps 10 billion resembling Earth. For every grain of sand on every beach, there may be a world. But with that abundance came a paradox, one as old as the question itself. If planets and potential habitats are so common, where is everyone? This question, first posed by physicist Enrico Fermi in 1950, has become one of the great mysteries of science, the Fermi paradox. By all probability, intelligent life should be widespread. Yet we see no evidence, no signals, no artifacts, no signs of visitors. The cosmos, for all its immensity, remains silent. For decades, the search for extraterrestrial intelligence SETI has been listening for whispers in that silence. Using radio telescopes like Arecibo and the Allen Telescope Array, scientists have scanned millions of frequencies, searching for patterns that could not arise naturally. They have found signals, tantalizing ones, but all, so far, have dissolved under scrutiny. Some were pulsars, others satellites, and many were simply noise. But the search continues, now broader than ever. SETI's modern incarnation no longer listens for a single narrowband transmission but scans for broader technosignatures. Waste heat from megastructures, atmospheric pollutants, artificial light on planetary nightsides. The logic is simple. If life evolves into technology, it must leave footprints. Yet, despite decades of searching, no clear evidence has emerged. Many of these worlds orbit small, active stars that blast them with radiation. Some are tidally locked, with one hemisphere forever in daylight and the other in endless night. Life there, if it exists, would be unlike anything we know, adapted to extremes beyond imagination. As our instruments improved, so did our ability to read the atmospheres of these distant worlds. Many of these worlds orbit small, active stars that blast them with radiation. Some are tidally locked, with one hemisphere forever in daylight and the other in endless night. Life there, if it exists, would be unlike anything we know, adapted to extremes beyond imagination. As our instruments improved, so did our ability to read the atmospheres of these distant worlds. To some, this is disheartening. To others, it's humbling. The universe is not obliged to make sense to us. The physicist Neil deGrasse Tyson once said, "Perhaps we are still listening with primitive ears, or perhaps we have misunderstood what intelligence looks like." The discovery of exoplanets has also deepened our understanding of planetary diversity. When a planet transits its star, a fraction of starlight passes through its atmosphere, imprinting spectral fingerprints of gases like oxygen, methane, and carbon dioxide. Detecting such a combination, a biosignature, would be the closest thing to proof of life we could achieve from afar. Already, the James Webb Space Telescope, JWST, has begun to do just that. Its infrared eyes can analyze light with unprecedented precision. In 2023, JWST detected carbon dioxide and even potential signs of methane on several exoplanets. The data remain ambiguous. There are many non-biological explanations, but it marks a turning point. For the first time, we are studying the chemistry of alien skies. And still, the silence persists. Some scientists suggest the silence might not be real at all, that we are simply too early. The galaxy is 13 billion years old, and humanity's radio presence extends only about 100 light-years, a microscopic bubble in galactic terms. Perhaps civilizations are rare and brief, their signals fleeting, their stories short. Perhaps they communicate in ways we cannot yet perceive, through neutrinos, quantum entanglement, or something beyond physics as we know it. Others suggest a darker explanation, that civilizations, once reaching a certain level of technology, inevitably destroy themselves. Nuclear war, climate collapse, or runaway artificial intelligence could end them before they ever reach the stars. If that's true, then perhaps the silence we hear is the echo of extinction, a universal pattern written into the evolution of intelligence. Yet there is a gentler possibility. Maybe the universe is alive, but it values its privacy. Intelligent beings might avoid broadcasting themselves, fearing the unknown. Just as we look outward, they might be listening too, both sides waiting for the other to speak first. Meanwhile, our own planet has become a beacon. Every radio wave, every television broadcast, every radar pulse has been leaking into space for nearly a century, forming an expanding shell of signals now 100 light-years across. Somewhere, perhaps, another civilization is tuning in, puzzled by faint whispers from a small blue world orbiting an unremarkable star. The irony is that as we search for others, we also begin to see ourselves more clearly. The fragility of Earth, its thin atmosphere, its narrow balance between warmth and cold, reminds us that habitability is precious. The cosmic silence forces a kind of introspection. If we are alone, then we are the voice of the universe itself. And if we are not, then somewhere right now someone else is looking up, asking the same question. We stand at a threshold. For the first time in history, our technology can detect the faintest traces of distant life. An oxygen molecule, a methane signature, a whisper of heat. And perhaps, one day, that data will reveal the impossible. Confirmation that we are not alone. But the search also brings a new humility. In the endless ocean of stars, our entire civilization is a flicker. The great silence may not be absence, it may be time, distance, or simply scale. The universe speaks in millennia. We have been listening for a heartbeat. Still, we keep listening, because within that silence lies possibility. And as telescopes reach farther, and spacecraft journey deeper into the outer dark, the next great discovery may come not from sound, but from sight, a reflection, a shimmer, a signal written in light. The next chapter of exploration would no longer be about the solar system, but about systems of suns. And yet, as humanity's gaze turned outward toward the galaxy, another story began to unfold closer to home. A story of a small, pale world whose future might depend on what we learn from the stars. Part 9. The Fragile Blue. Earth, Climate, and the lessons of the planets from space. Earth glows with an impossible beauty, a marble of blue and white suspended in darkness. It is the only world we know that breathes, where water flows freely, where clouds shift and reform in endless motion. Yet this very familiarity blinds us. We forget how rare such balance is. The story of the solar system, of Jupiter's storms, Mars's desolation, Venus's inferno, and the frozen oceans of Europa and Enceladus, is not just about other worlds. It is increasingly a mirror of our own. Every planet tells a cautionary tale, a version of what might have been, or what could yet become. When Voyager 1 turned its camera back toward Earth in 1990, from 6 billion kilometers away, it captured the most humbling image in human history. A speck of light suspended in a sunbeam. "That's here," Carl Sagan wrote. "That's home." Every human being who ever lived there. The pale blue dot became both a symbol and a warning, a reminder that our planet, for all its vastness, is fragile. Over the last century, we have begun to measure that fragility. Greenhouse gases trap heat in the atmosphere. Oceans absorb carbon and grow acidic. Ice sheets melt into the sea. For the first time, humanity's influence rivals geological forces. We are reshaping the climate faster than any natural process in Earth's recent history. But in understanding other planets, we have also begun to understand ourselves. Venus, our sister world, offers a glimpse of what happens when a planet's balance tips too far. It is almost identical to Earth in size and composition, yet its atmosphere is a crushing shroud of carbon dioxide, over 90 times denser than ours. Surface temperatures reach 460 degrees Celsius, hot enough to melt lead. Its clouds are sulfuric acid, its landscape, a furnace. Once, Venus may have been temperate. Some models suggest it could even have had oceans billions of years ago. But a runaway greenhouse effect turned it into hell. The sunlight that reached its surface was trapped by CO2, heating the atmosphere, evaporating water, and releasing more carbon in a spiral of destruction. The lesson is stark. Climate can change not gradually, but catastrophically. Mars tells the opposite story. Once warm and wet, it lost its atmosphere to space, stripped away by solar winds when its magnetic field died. Without protection, the planet cooled, its water froze or evaporated, and its rivers dried. Where Venus burned, Mars froze. Between them, Earth alone survived in the narrow corridor of stability. For decades, planetary scientists have drawn parallels between these worlds and our own. What happened to Venus and Mars is not distant history. It is a study in planetary thermodynamics, a demonstration of how delicate the balance of temperature, pressure, and chemistry truly is. Earth's climate is self-regulating, but only within limits. We are now testing those limits. From orbit, satellites measure our planet's changing face. Retreating glaciers, rising sea levels, forests breathing carbon and then choking on fire. Instruments track methane leaking from the Arctic and carbon dioxide increasing year by year. The numbers are precise, and the trend is unmistakable. Yet, paradoxically, it is the view from space that brings clarity. Astronauts aboard the International Space Station often describe the overview effect, a profound shift in perception when seeing Earth from above. They speak of its fragility, of thin blue lines that mark the atmosphere, of storms swirling over continents. It is a reminder that borders and politics vanish at altitude. There is only one world, fragile and alive. Dr. Mae Jemison, the first African-American woman in space, once said, "When we look at the Earth from space, we see ourselves as one system. We are all connected, and that connection is both our greatest strength and our greatest responsibility." The study of other worlds deepens that sense of connection. Jupiter's magnetosphere shields the inner solar system from some cosmic radiation. Saturn's gravity shapes asteroid belts. Comets deliver water and carbon to terrestrial planets. Even the chaos of the outer giants contributes to the harmony of the whole. The solar system is not a collection of isolated worlds. It is a living, gravitational ecosystem. And Earth is part of it. That perspective has transformed climate science. By comparing Earth with Venus, Mars, and Titan, scientists can test atmospheric models under extreme conditions. Venus teaches us about greenhouse dynamics, Mars about atmospheric loss, Titan about methane cycles. Together, they form a comparative laboratory of climates, and Earth the control experiment. Yet, as data mounts, so does a sense of urgency. Climate change is not theoretical. It is visible in melting ice and burning forests. Sea levels rise, seasons shift, and species vanish. For the first time, we are witnessing in real time the kind of transformation that once took eons. Still, there is hope in knowledge. The same technologies that study distant worlds now monitor our own. Instruments that mapped methane on Mars now track it on Earth. Algorithms designed to analyze exoplanet atmospheres are repurposed to study pollution and cloud cover here. The science that reaches for the stars is, ironically, what may help save the planet beneath our feet. The story of exploration is also the story of reflection. Every mission launched outward eventually turns back. Pioneer 10 carried a golden plaque. Voyager carried a golden record with music, greetings, and images of Earth. Even Juno, orbiting Jupiter, carries small aluminum figurines of Galileo and the Roman god it was named after. Every time we send something into the void, we embed a piece of ourselves, not out of arrogance but out of yearning. Because at the heart of exploration is a paradox. We go outward to understand inward. When we study Jupiter's storms, we learn about energy and motion. When we measure Mars's dryness, we learn what water means. When we gaze upon Europa's ice, we see how precious our oceans are. Each discovery beyond Earth returns home as wisdom. And so, the pale blue continues its slow turn beneath the sun, a fragile oasis guarded by chance and physics. The storms of Jupiter, the fires of Venus, the silence of Mars, all serve as reminders of what can be lost. The challenge now is not just to explore, but to endure, to ensure that the species capable of sending its machines to the edge of the solar system does not forget the world that gave them birth. We have peered into the atmospheres of other planets and seen both doom and promise. The lesson is not despair but vigilance, the realization that stewardship is not an option but a necessity. And perhaps that is the truest meaning of exploration. Not conquest, not discovery for its own sake, but preservation through understanding. Because in the end, the same forces that shape the stars also shape us. The same chemistry that burns in Jupiter's storms burns in our veins. The universe is not elsewhere. It is here, looking back at itself through human eyes. From this vantage point, one truth becomes inescapable. To save the Earth is to save the only voice the cosmos has ever used to describe itself. Part 10. The Chain of Worlds. How the solar system became our mirror in every direction we look. From the boiling clouds of Venus to the frozen plains of Pluto, the solar system tells a single, interconnected story. It is not a story of separate worlds, but of continuity. A cosmic family bound by gravity and time. Each planet, each moon, each asteroid is a fragment of one great experiment, the evolution of matter into complexity, and perhaps into consciousness. For centuries, we studied these worlds in isolation. Jupiter was the king, Saturn the jewel, Mars the warrior, Earth the cradle. But as our telescopes sharpened and our spacecraft ventured outward, the lines blurred. We began to see patterns, geological, chemical, magnetic, that tied them together. Slowly, the solar system stopped being a collection of curiosities and became a mirror. A reflection of processes, of histories, and ultimately of ourselves. Consider the chain of worlds that orbit the sun. Mercury, baked by radiation, is a scarred remnant of the sun's early violence. Venus is a warning, the same ingredients as Earth, but with the thermostat turned too high. Earth itself is the rare middle ground, a masterpiece of balance. Mars is the ghost of a possible twin, frozen and faded. Beyond them, Jupiter and Saturn are cosmic anchors, their gravity shepherding comets and shielding the inner planets from catastrophe. Farther still, Uranus and Neptune, giants of ice and methane, mark the edge of the known, where the sun becomes a distant star. But to see these worlds only as they are is to miss the deeper revelation. They are not static. They are stages in a vast continuum, snapshots of what planets become over billions of years. In them, we glimpse our past and our possible futures. Mercury shows what happens when a planet's atmosphere is stripped away by solar wind. Venus demonstrates the chaos of a runaway greenhouse effect. Mars reveals the slow death of a world that lost its magnetic field. The gas giants teach us how worlds can form in excess, enormous, unstable, yet essential for shaping smaller, habitable ones. Even the moons, Europa, Enceladus, Titan, remind us that life does not belong only to the surface, but may hide beneath it, waiting for warmth. This pattern, destruction, preservation, renewal runs like a thread through the solar system. It mirrors the same forces that govern stars, galaxies, and life itself. Creation and decay, heat and cold, chaos and order. It is not coincidence. It is physics written in the language of time. And yet, amid that vast machinery, one world, our world, stands out. Not because it is central, but because it is conscious. Earth has become the mirror in which the universe sees its own reflection. Through us, the cosmos examines itself. This realization has transformed the very way we conduct science. Once, planetary exploration was about conquest, about reaching farther, planting flags, claiming firsts. Now, it is about connection. Each mission adds a piece to the larger mosaic, revealing how planets influence one another, how their fates intertwine. When Juno measures Jupiter's magnetic field, it helps us understand how Earth's works. When Cassini observed Saturn's rings, it taught us about the early formation of planets, the same process that built our own. When InSight listened to quakes on Mars, it refined our models of planetary interiors, giving us better tools to predict earthquakes here. Every discovery out there echoes back home. We have learned that planets are not isolated islands, but nodes in a network of gravitational and chemical exchange. Comets deliver water. Asteroids carry carbon. Magnetic fields sculpt solar winds. The boundaries between worlds are porous, blurred by radiation and dust. The solar system is not a collection of separate entities. It is a single, interwoven organism, alive with motion. Even light, the one constant that unites them all, behaves differently across its expanse. The sun's rays warm the rocky planets, shimmer off the gas giants, and fade to a whisper among the ice. Yet in that fading, they still connect. Photons that left the sun 8 minutes ago now bounce from a spacecraft orbiting Saturn, carrying back data, reflections, and proof of continuity. It is a kind of dialogue, though not in words. A gravitational conversation spanning billions of kilometers, where each world contributes its note to a cosmic chord. And what of us, the listeners? Our telescopes are ears pressed to that chord, trying to decipher meaning. Our spacecraft are emissaries of curiosity, tracing invisible threads of force and chemistry. In doing so, we've discovered that the solar system's greatest revelation is not alienness, but familiarity. Look long enough at Jupiter's auroras, and you see echoes of Earth's own polar lights. Study Saturn's storms, and you glimpse the same dynamics that shape our hurricanes. Analyze Mars's dust devils, and they behave like miniature cousins of our desert whirlwinds. The physics repeats, scaled by gravity and distance, a universal grammar of motion. This repetition brings comfort and humility. The same laws that sculpted Saturn's rings carved the Mississippi River. The same processes that froze Europa's ocean gave us glaciers. The cosmos is not something apart. It is something we are part of. In this sense, exploration has never been about finding the other. It has always been about rediscovering the self. The solar system, in all its diversity, is a vast hall of mirrors reflecting variations of one truth. That matter, under the right conditions, organizes itself into complexity, and that complexity, under the right circumstances, begins to ask questions. And so, as we study these distant worlds, we also study evolution, not just of planets, but of perception. From the myths that once named these bodies as gods, To the algorithms that now map their atmospheres, our understanding of them reflects the evolution of our species. From wonder to measurement, from faith to evidence, from isolation to belonging. This recognition has reshaped even the philosophy of exploration. No longer do we see the solar system as a ladder to climb, one world after another, but as a web to understand. Its strength lies not in its hierarchy, but in its interdependence. The chain of worlds is, in truth, a circle, a self-sustaining loop of cause and effect that includes us. The comets that seeded Earth's oceans may have come from beyond Neptune. The atoms in our bodies, forged in ancient stars, were once scattered through clouds of interplanetary dust. We are not visitors here. We are made of the same matter we study. To explore the solar system, then, is to come home. And that home is vast, filled with storms that never end, ice that hides oceans, and silence that hums with potential. Each world reflects a different possibility, a different chapter in the long experiment of existence. As our probes drift farther outward, to Uranus, Neptune, and beyond, the chain of worlds grows longer, stretching toward the unknown. And perhaps, somewhere beyond the heliosphere, there are others, systems like ours, suns like ours, lives like ours. But before we look outward again, there is one final lesson still to learn. How it all began. The solar system is not eternal. It was born from collapse, from chaos, heat, and dust. Understanding that beginning may reveal not only where we came from, but how rare we truly are. Part 11, Genesis of Light. The birth of the solar system before there were planets, before there was sunlight, before even the sun itself existed. There was only a cloud, cold, dark, and ancient. It drifted quietly among the stars, a vast nebula of hydrogen, helium, and trace dust, remnants of generations of stars that had lived and died long before ours. This cloud was unremarkable, one among billions in the Milky Way. Yet within it lay the ingredients for everything, for oceans, for worlds, for life. The story of the solar system begins in collapse. Perhaps it was triggered by the shockwave of a nearby supernova, or perhaps by the slow hand of gravity itself. Whatever the cause, somewhere in that quiet cloud, a ripple began. Particles drifted closer, then closer still until they began to fall inward. The collapse accelerated. The nebula spun faster and flattened into a disk, a cosmic whirlpool of gas and dust spiraling toward the heart of what would become the sun. At the center, pressure and temperature rose until hydrogen atoms fused into helium. In that moment, light returned to the darkness. The newborn sun ignited, and the solar system took its first breath. Around it, the disk glowed faintly, divided into zones by temperature. Near the sun, it was too hot for anything but metals and silicates to solidify. Farther out, where it was cooler, ices of water, methane, and ammonia condensed. In that thermal gradient lay the blueprint for every world that followed. Tiny grains of dust began to collide, sticking together through static and chance. Over millions of years they grew, from pebbles to boulders, from boulders to planetesimals. The collisions were violent. Some shattered, others merged, and a few became large enough for gravity to shape them into spheres. The solar system was a battlefield then, a place of fire and impact, where orbits shifted and worlds competed for survival. In the inner regions, rocky planets formed. Iron sank to their cores, silicates rose to their crusts, and thin atmospheres clung precariously to their surfaces. Mercury, Venus, Earth, and Mars, four worlds born from the same dust, each taking a different path. In the outer disk, gravity worked on a grander scale. Jupiter formed first, sweeping up gas and dust like a cosmic vacuum cleaner, its massive pull shaping the orbits of everything else. Saturn followed, adorned with the icy remnants that would one day form its rings. Beyond them, Uranus and Neptune coalesced in the cold, giants of ice and gas, slow to form, distant and quiet. But the story was not gentle. In those early days, the young solar system was chaotic. Hundreds of planetary embryos roamed unstable orbits. Asteroids and comets bombarded the inner worlds. one of those collisions, colossal beyond comprehension, struck the newborn Earth, ejecting molten debris that would coalesce into the moon. The scars of that violence remain written across every rocky surface we've ever explored. The craters of Mercury, the basins of the moon, the scars of Mars. Over time, the chaos subsided. The sun stabilized, the remaining dust was swept away by solar wind, and the surviving planets settled into orbits that, remarkably, have endured for billions of years. The solar system, once a storm of creation, became a system of order. But the process was not merely mechanical. It was chemical and it was subtle. Within that protoplanetary disk, carbon combined with hydrogen to form methane, nitrogen with hydrogen to form ammonia, oxygen with hydrogen to form water. These simple molecules condensed into comets and asteroids, carrying the seeds of organic chemistry. When these icy bodies later bombarded Earth, they delivered water to its surface and carbon to its crust. Out of cosmic debris came the conditions for life. Every ocean, every cloud, every living cell owes its existence to that ancient rain of comets. We are, quite literally, the residue of stardust. Even now, echoes of that genesis remain. In the Kuiper belt beyond Neptune, frozen relics like Pluto and Eris preserve the chemistry of the early solar system. Farther still, in the Oort cloud, a vast, spherical shell extending trillions of kilometers, comets linger, untouched since the dawn of time. Each one is a time capsule, carrying the same ices and organics that once built the planets. When they fall inward toward the sun, their tails of vapor are not just beautiful, they are reminders of our beginning. To study the formation of the solar system is to look into a mirror of origins. The same physics that shaped our world operates everywhere in the universe. Around other stars, disks of dust are coalescing even now. The Atacama Large Millimeter Array ALMA in Chile has captured images of such systems, concentric rings of gas and dust, astonishingly familiar, surrounding young suns. We are watching in real time the birth of other solar systems, and in that observation lies a deeper truth. Our story is not unique. It is universal. Wherever matter gathers, gravity sculpts, chemistry plays, and light ignites, there worlds will form. And among those worlds, some will cool enough for oceans, and some of those oceans will stir. Still, what happened next on Earth remains singular in our knowledge. Life took hold. Perhaps it began in the shallow pools of a young ocean, perhaps near hydrothermal vents deep beneath the waves. Maybe it was sparked by lightning, or seeded from comets carrying prebiotic molecules. However it happened, it was the continuation of a cosmic process, matter organizing itself toward complexity. Life, in this sense, is not an exception to the universe. It is an expression of it. Yet the solar system's creation story is also a reminder of impermanence. The same sun that birthed its planets will, one day, destroy them. In roughly 5 billion years, it will exhaust its hydrogen, expand into a red giant, and swallow Mercury and Venus. Earth will burn. The outer worlds will drift into darkness. Eventually, the sun will shed its outer layers and shrink into a white dwarf, a glowing ember surrounded by the cold remnants of what was once a family of worlds. That, too, is part of the pattern. Stars die, but their deaths scatter heavy elements, carbon, oxygen, iron, into space. From those ashes, new stars and planets will form. The cycle will begin again. In that endless renewal lies the universe's quiet resilience. When we look up at the night sky, every star we see is a potential cradle of such creation. Somewhere, right now, another cloud is collapsing, another sun is igniting, another set of worlds is forming. And somewhere on one of those worlds, perhaps life is beginning, not knowing yet that it is part of something vast and ancient. The solar system's birth was not a singular miracle. It was one verse in an infinite cosmic symphony, a song of dust and fire that repeats across galaxies. But for us, it is the first verse, the one that gave rise to everything we are. The planets, in their quiet revolutions, still carry the memory of that beginning, in their orbits, in their chemistry, in their storms. And so, In studying them, we are not just looking outward. We are remembering. Because in every sense that matters, we are not merely children of Earth. We are children of the Sunday Part 12, the echo of creation. The future of exploration and the fate of discovery. When Voyager 1 crossed the boundary of the heliosphere in 2012, leaving behind the influence of the Sun for the first time, it entered a realm where no human-made object had ever been. Out there, beyond the faint pressure of sunlight, the spacecraft drifted into interstellar space, still whispering back data through a signal weaker than the glow of a watch battery. In that faint voice, we heard something extraordinary. The echo of creation itself. The journey of Voyager is more than a scientific triumph. It is a symbol. It represents what we have become. A species no longer confined to one world, reaching out across the void not out of conquest, but curiosity. Each mission we send, from Juno to James Webb, is an extension of that same question first asked in the darkness of prehistory. What's out there? The answer, it turns out, is everything. Yet, as our machines travel farther, our vision grows paradoxically inward. The deeper we explore space, the more clearly we see our origins and our limits. Every new world we visit reflects a piece of our own story, as though the universe were showing us fragments of a grand mosaic that we must piece together one discovery at a time. The next century of exploration will likely be defined by this dual vision, outward toward the stars, and inward toward understanding what life really is. The most immediate frontier lies within our own solar system. In the coming decades, Europa Clipper will orbit Jupiter, sampling plumes that might carry the chemistry of alien oceans. Dragonfly, a nuclear-powered drone, will soar through the thick orange atmosphere of Titan, searching for organic complexity on Saturn's largest moon. NASA's Mars Sample Return mission will attempt something audacious: to bring rocks from Mars back to Earth, letting us examine another world in our own laboratories. Beyond that, the line between robotic and human exploration will blur. Artemis missions are preparing to return astronauts to the Moon, not just for brief visits but for permanence. The lunar South Pole, rich in frozen water, will become humanity's first outpost beyond Earth. From there, the next logical step will be Mars, a goal that, for the first time, feels within reach. But colonizing another planet is not just an engineering challenge. It is a philosophical one. What does it mean to carry life, biological and cultural, to a place that has known only silence? When we touch the Martian soil, we will become part of its history, and it of ours. The moment we step there, the line between Earth and elsewhere will blur forever. Still, even Mars will be only the beginning. New propulsion concepts, nuclear thermal engines, plasma drives, even theoretical solar sails, promise to cut travel times to the outer planets. Missions like Interstellar Probe are being designed to follow Voyager's path intentionally, to cross into the interstellar medium while instruments still function. These craft could, within this century, send back data on the very edge of the Sun's influence, the true border between our system and the galaxy beyond. Meanwhile, our telescopes will continue their transformation from observers to explorers. The James Webb Space Telescope has already begun scanning the atmospheres of exoplanets for signs of life, methane, oxygen, carbon dioxide in the right proportions. Its successors, like NASA's proposed Habitable Worlds Observatory, will go further, using coronagraphs to block starlight and reveal Earth-like planets directly. For the first time, we may see the glint of oceans on alien worlds, the spectral fingerprints of chlorophyll or oxygen, evidence that we are not alone. When that day comes, it will be both a scientific and existential revolution. To detect life beyond Earth would not diminish our significance. It would expand it. It would mean that life is not an anomaly, but a pattern, a natural outcome of the universe's chemistry. It would mean that creation, in all its forms, is universal. Yet there is another possibility, one more haunting, but no less profound, that we find nothing. That every signal we detect is silence, every exoplanet barren, every ocean sterile. In that scenario, the universe would remain magnificent, but lonely, a cathedral without a choir. If that turns out to be true, then life on Earth, fragile, flawed, luminous, becomes even more precious. We would be the universe's only witness, the only voice capable of understanding its beauty. The responsibility of survival, then, would not just be ours but existence's itself. Either way, the quest continues. Humanity has never been good at standing still. From the first sparks of fire to the first radio transmission, curiosity has been our defining trait. And now, in the age of interplanetary reach, that curiosity has become a new kind of instinct, the need to know even if the answer humbles us. The irony of progress is that the more we learn, the smaller we feel. Our galaxy contains hundreds of billions of stars. Our universe, trillions of galaxies. The distances defy comprehension. Even if we traveled at light speed, it would take over 4 years to reach the nearest star. And yet, across those impossible gulfs, we send our small emissaries. Fragile, gold-plated, full of hope. Each probe carries something of us. A plaque, a record, a message. Voyager's golden record contains greetings in 55 languages, the sound of wind, rain, and heartbeat, and a map to our star. It is, in a sense, the first self-portrait of our species, not as conquerors but as participants in a greater story. Somewhere, a billion years from now, it may still drift intact, a relic of a civilization that once looked up and wondered. In the quiet between the stars, that record may outlive us all. And perhaps that is the true echo of creation, not in the noise of beginnings, but in the endurance of meaning. The same universe that forged the atoms in our blood has given us the capacity to understand them. In that understanding lies continuity, the knowledge that the cosmos is not indifferent because we, who are of it, can care. The future of exploration will not be defined by how far we go, but by how deeply we connect. Whether we find life on Europa or silence in the stars, every discovery brings us closer to seeing ourselves as part of a single unfolding narrative, one that began in a cloud of dust and now stretches toward eternity. One day, our descendants may stand beneath a different sky, perhaps on Mars, perhaps beyond, and look back toward the small, pale light of home. They will see Earth not as a boundary, but as a beginning. And when they do, they may finally understand that the greatest journey was never through space at all, but through awareness, the long awakening of a universe learning to see itself. Part 13. The Long Tomorrow. Humanity's destiny among the stars. Every age of exploration begins with a question, and every new horizon reveals that the question was too small. For centuries, humanity's frontier was the ocean. Then it became the sky. Now it is the void between the stars. And just as our ancestors once built ships to cross the great seas, we are beginning to build ships for the darkness. Fragile arcs of metal and light, carrying the oldest dream of all, to endure. The question that drives us now is not merely where can we go, but how long can we last? Even in our optimism, we know that Earth is finite. The sun will expand. The planet will warm. The continents will shift and the seas will rise. Whether in 100 years or a billion, every world, every species faces an ending. But life, especially intelligent life, has always defied endings. It adapts, transforms, and continues. And perhaps that is the destiny of our kind, to become the mechanism by which Earth itself survives its limits. In this vision, humanity is not an intruder in the cosmos but its instrument, the branch of the universe that has learned to move itself. Already, the outlines of that destiny are forming. The moon is no longer a distant dream but a destination of industry and science. Mars, once myth, now glimmers with robotic eyes and tire tracks. On its rusty plains, we have begun to test the first seeds of off-world survival. Habitats grown from regolith, oxygen extracted from atmosphere, power drawn from sunlight. The first generation born under a different sky may already be alive today. But Mars will not be the end. It will be our apprenticeship, the first step in learning how to live among worlds. Beyond it lies the asteroid belt, rich in minerals and metals. Beyond that, the moons of Jupiter and Saturn, each a laboratory of chemistry and ice. And beyond them still, the Kuiper Belt, a vast frontier of frozen resources and ancient matter. If history is a guide, we will go where curiosity leads first, and where necessity drives second. The same restlessness that carried us from caves to continents will one day carry us beyond the heliopause, into the dark between stars. The first interstellar journeys will not be human in the flesh. They will be robotic, autonomous explorers built to endure centuries. Voyager was the first prototype of this lineage. The next generation may be small, sail-powered craft like those envisioned by the Breakthrough Starshot initiative, wafer-thin probes accelerated by powerful ground-based lasers to a fifth of the speed of light. At that pace, they could reach Alpha Centauri in just over 20 years. They would send back images, data, and perhaps the first confirmation that another world, orbiting another sun, holds oceans like ours. But if such worlds exist, and we now know that many do, the leap from visiting to inhabiting will challenge everything we know about biology, engineering, and identity. For a human body, even Mars is hostile. Radiation, isolation, low gravity, each erodes us in subtle ways. To reach the stars, we will need to change ourselves as much as our machines. Genetic adaptation, cybernetic enhancement, artificial intelligence, once the realm of science fiction, will become necessities. The future traveler may not be entirely human as we define it today. Perhaps that is fitting. Evolution has never been static. We are simply its next iteration, sculpting ourselves consciously for survival. Yet amid the technology, the essence of exploration will remain what it has always been: wonder. Imagine a night on a world orbiting another sun. The air thin but breathable, the horizon curved differently, the constellations unrecognizable. Imagine the first human standing there, looking up and realizing that the light of Earth's sun is now a star among thousands, just another speck in an unfamiliar sky. That moment will be the culmination of every question, every launch, every orbit traced since Pioneer 10 first crossed the asteroid belt. And yet, even then, the same question will persist. Are we alone? It is likely that we are not. The galaxy is too vast, its chemistry too consistent, its opportunities for life too abundant. But contact, true contact, may be forever beyond our reach. The distances are merciless. Even light, the fastest messenger, takes years to cross from star to star. If civilizations exist, they may rise and fall within the gaps of time it takes their signals to arrive. The cosmos may be full of voices, but each separated by centuries of silence. If so, perhaps that silence is not tragedy but design. The universe may be a garden of civilizations, each blooming in solitude, each carrying the same sense of wonder, each looking outward and finding peace in not knowing. But solitude is not isolation. Through our telescopes and instruments, through mathematics and art, we are already connected. Every act of discovery, every equation written, every image captured by a distant probe, is a thread woven into the fabric of a collective cosmic consciousness. Our destiny, then, may not be to conquer the stars, but to understand them, to become their historians, to witness, to remember, to give meaning. The philosopher Teilhard de Chardin once wrote that the history of the universe is the history of consciousness rising toward self-awareness. In that sense, every star we study, every planet we name, is the universe becoming aware of itself. We are not apart from the cosmos. We are its awakening. Still, destiny is not guaranteed. The challenges before us, climate, war, inequality, indifference, are as formidable as any distance between stars. Technology alone will not save us. The survival of our species depends not only on intelligence but on wisdom, the ability to see beyond the next generation, the next prophet, the next border. If we cannot learn that here, we will carry our conflicts with us into the stars. The next great leap, therefore, is not technological but moral. To become a spacefaring species, we must also become a compassionate one. When the Voyager spacecraft left Earth, it carried a message written for unknown listeners. Perhaps no one will ever hear it. But that message was as much for us as for them, a declaration of who we were when we first reached beyond the cradle. On that record is a child's laugh, a heartbeat, and the sound of rain. It is not power we chose to send into the dark. It is tenderness. that may be our truest legacy. One day, billions of years from now, when the sun has dimmed and the memory of Earth has faded, some fragment of what we were may still be drifting between the stars. A probe, a pattern, a story. And in that story will remain a simple truth, that for a brief moment in cosmic time, matter learned to wonder about itself. The universe will go on. Stars will be born and die. Worlds will form and vanish. But the echo of that wonder, the human question, will endure. And perhaps, somewhere far ahead, in another era, another species will find that echo, decipher it, and know that once, long ago, a civilization of dreamers reached into the dark and whispered, "We were here. We saw. We understood." And in that whisper, the long tomorrow will begin again. Part 14. The Last Light. Legacy, memory, and the endless unknown in the end. All stories return to silence. Stars fade, worlds cool, and light, the most constant witness, begins to dim. Yet even in that silence, memory endures. The cosmos forgets nothing. It only transforms. Energy becomes matter. Matter becomes dust. Dust becomes light again. In this endless cycle, everything that has ever existed continues in another form. Perhaps that is what legacy truly means. Not the monuments we build, but the traces we leave woven into the larger pattern of existence. When Voyager 1 sent back its final transmission from beyond the heliosphere, its faint pulse took over 20 hours to reach Earth. It was data, electric whispers encoded in binary, but it was also poetry, proof that something made by human hands had crossed into the interstellar dark and was still speaking. In that signal, we heard not just the machine's endurance, but our own reflection. The last light of the sun will one day fade too. In 5 billion years, it will swell into a red giant, its brilliance both creation and destruction. Mercury and Venus will vanish into its fire. Earth will be stripped bare, its oceans boiled away, its rocks turned to vapor. But even as the sun consumes itself, it will cast its final light far across the solar system, across Jupiter's storms, Saturn's rings, the distant ice of Pluto. For a moment, the entire system will glow as if remembering what it once was. And then the light will dim. After the sun collapses into a white dwarf, its heat will fade slowly over trillions of years. The planets, if they survive, will drift farther out, their orbits stretching like forgotten threads. The stars around us will move on. The constellations will dissolve. The Milky Way itself will change shape, its spiral arms merging, its stars aging. But perhaps there will still be eyes to see. By then, if humanity endures, we will have long outgrown the solar system. We will have learned to live among the stars, to harness the light of other suns, to travel in ways that defy our current imagination. Our descendants, biological, digital, or something beyond, will not look back in grief, but in gratitude. They will remember that they came from a small blue world that once orbited an ordinary star, and that everything they became began there. Even if humanity itself is gone, even if we vanish as countless species before us have, something of us will remain. Our machines, our signals, our artifacts will continue drifting outward. The golden record aboard Voyager will circle the galaxy for 1 billion years, carrying music and laughter, languages and love, fragments of a civilization that dared to reach beyond its limits. And perhaps, somewhere far away, another intelligence will find it. Perhaps they will play its sounds and hear, faintly, the heartbeat of a creature that once gazed at the night and asked why. That question, that simple, luminous question, is the true legacy of our species. We have built civilizations, mapped genomes, decoded light from galaxies billions of years old. But beneath it all, the impulse is the same: to understand. To not simply exist, but to know existence. In that pursuit, we have learned something profound: that knowledge and wonder are not opposites, but partners. Science does not erase mystery. It refines it. The more we learn about the universe, the more beautiful it becomes, because understanding does not diminish awe, it deepens it. Our ancestors once saw the heavens as a realm of gods. We now see them as a realm of laws, forces, and particles, and yet the feeling they inspire is unchanged. To gaze upon the Milky Way from a dark horizon is still to feel small, and yet profoundly connected. It is this duality, insignificance, and belonging that defines the human spirit. We are dust and consciousness, ephemeral and eternal, bound by the same physics as the stars and yet capable of understanding them. In the very long view of time, everything we know will fade. Galaxies will collide, stars will burn out, black holes will evaporate. Even light itself may one day cease to move. The universe, so full of brilliance now, will fall into darkness, a final, quiet equilibrium. And yet, even then, something will persist: information. The patterns that once composed worlds, thoughts, and dreams will remain encoded in the quantum fabric of spacetime. Every photon ever emitted, every thought ever thought, will exist forever as a ripple in the cosmic field. In that sense, nothing is ever truly lost, it only changes its form. Perhaps, in that far future, another cycle will begin. Perhaps new universes will bud from the old, like seeds from a dying tree. And somewhere, in the newborn light of another cosmos, the pattern that once was us will arise again, not as memory, but as renewal. If that is true, then our legacy is not a monument, but a rhythm. A resonance between what has been and what will be, the echo of creation, carried forward through the endless transformations of time. And maybe that is what we were always meant to be, not conquerors of the cosmos, but participants in its continuity. A brief flicker of awareness that, for one miraculous moment, knew it was part of something infinite and cherished that knowledge. So when the last light of the sun fades, and the stars of the Milky Way whisper their final photons into the dark, somewhere, something will still remember. The universe itself will remember because for a time it looked back at itself through our eyes. We are not the beginning nor the end. We are the light between them,